Today, first lecture will be some Matlab demonstrations. We are missing a couple of examples in the book by Fritz, showing you a little bit more about the effect of a upwind scheme. So I would say roughly 1 hour there. Second hour, I suggest we play around with open foam, go a little further. We have to continue there tomorrow. It will be more exercise-like, a little bit theory, well, demonstration more with open foam in preparation for exercise number 3. But today it will then be these examples. You find them in the end of chapter 4 somewhere. If this one works. No, it doesn't. Okay. Open with something else. Here we go. Chapter 5. Here we go. We haven't actually started the topic with finite volume yet. We are only focused on finite difference. So the finite volume, the starting point is quite different. You don't start with a differential equation, you start with an integral equation. And we will come back to what's important there. This one covers more physics actually. You can have jump inside your domain, and that's allowed. In a differential equation, it has to be a continuous function. You can't have a sudden jump like a shock wave or something like that inside your domain. Then you have to do some dirty tricks. But for now, just trust me when I say the algebraic equations we end up with using finite volume will be identical to the finite difference as long as we are using a rectangular mesh, delta x equals delta y, then everything should be a-okay. Here, of course, you see delta x not constant, it changes. So that's not for us yet. So we just use a rectangular mesh, then everything should be a-okay. You can read this theory here if you like. I'll have just an excerpt of it later, the important part. For now, we will jump to the examples. A couple of examples here. And the starting point, again, it's sort of our Advection diffusion equation. If you look at it, the velocity field is given. That one is known. So here we have a sort of an integral of the unknown phi around a surface. Also here, surface integral of this gamma, the diffusion coefficient, and then the gradient of our unknown in the normal direction of the surface S. So how to achieve that equation? Well, of course, a little bit algebra. If you remember the starting point that we had last time, that was the Advection diffusion equation. So we had dx of rho u phi equals, and then ddx of gamma d phi dx, like that. That was the differential equation. And here it's a one-dimensional case, so you don't have to use partial derivatives. So what you do now, you take the integral of the entire equation with respect to x, and what do you get? Well, as you see, the first part there, he will now just simply be this surface integral. You will have an integral of a gradient, and also here integral of a gradient, which then you could trick around with the divergence theorem in 3 dimensions and go from a volume integral. I mean, here we have only 1 dimensional, but in full 3D it will be a volume integral. Then you jump from a volume integral to a surface integral, end up with this equation. We'll come back to that later. So yes, it is advection diffusion equation. For the first example, the velocity field is given. It's a 2-dimensional case. So velocity in the x direction is x, velocity in the y direction equals minus y. And if you write it like this, it's a fairly classical example that you typically find in the basic course in fluid mechanics. And if you want to have a look at what kind of flow we are talking about, it's the stagnation flow. It goes something like this. So the streamlines just becomes hyperbolas. Now the velocity field here is known, it's given. So the only thing we are worrying about now is this phi. And the phi here is, say, a concentration. And now we're only focusing on the first quadrant. We're only looking at what's happened here. So that is our problem. So here is the geometry, first quadrant. And then we say at the inlet here, we don't have any of this unknown phi. It's 0. And now along this left wall, you don't have any velocity perpendicular to the wall. You have a velocity alongside the wall, so it's not a no-slip condition here. It's sort of a free slip, yeah. You have a velocity alongside the wall. Here we have a variation of our unknown phi, the concentration. Goes from 0 to 1 at the bottom here. And now you might ask, how the heck can this concentration enter into this area here? If this is a solid wall and you send in 0 at the top, well, it's nothing to do with this advection term, the transport term. You have no transportation through a solid wall. You don't have a velocity through the y-axis. But this term, the diffusion term, he will sort of let this concentration diffuse into our area. So we should suspect a solution then with mostly zeros of this phi, but you will have something here more and more alongside this left wall, and then due to the flow he will be transported out. So we will have some phi in this matter. Here, just as I say, the velocity field is known. We know the streamlines before we begin. It's just this concentration we don't know. So our boundary conditions, 0 at the inlet at the top. We have this change from 0 to 1 on the left wall. And then we have symmetry line, and actually a symmetry line here also at the outlet. Normal derivative equal to 0. So then you're talking a Neumann condition. So this is the problem. And we use two different schemes. And here UDS, that is first order upwind, and a CDS, that is a central scheme, second order accurate. And as always, when you are thinking of the choice here, it is where you have a velocity where you can then decide which direction is the upwind. So it's this term you choose, upwind scheme or central scheme. This one, that is given. That is always a central scheme. You don't have an additional velocity here. You can't decide an upwind direction in this term. You need a velocity. Now let's see how this one looks. So here I have programmed it after the recipe and given in the book, and I have played around with some test cases. The number of unknowns, 100 by 100 and 40 by 40. So let's start with 40 by 40, just so it goes a little fast. Now the value of this gamma, the diffusion constant, the smaller it is, the harder it will be to solve. Think of it as a viscosity. So this a very, very small viscosity, well, this problem is going to turn into turbulent. It's impossible to solve. So the smaller he is, the more in trouble we will be when it comes to stability. If he's a very big one, it's a very sticky fluid, and it's like honey or something, very stable, no problem. So we start with him fairly small, 1/1000. And then it's a question how to solve our algebraic equation system. Here I have set up just the coefficients, and then I use an iterative scheme, and then using the SOR, the successive over-relaxation, the same one as we have in the Sola algorithm. But here I have to be careful. This omega, if you can recall, a good value was between 1 and 2. And the more unknown you had, the closer he should be to 2, to be optimum, to be fast, to be efficient. So, okay, let's try. We have a 40 by 40 case. And gamma, 1/1000. And my omega, we can start with 1.5, something like that. And now I choose the upwind scheme. It's more stable, should be easier to solve. And he crashes. So an omega here, over relaxation, it's more than just solving an iterative scheme. It's actually also something to do with stability, obviously. So to solve it here, I actually need quite a small one. I think 1.3 may be okay. Yeah, he survived. So here you have the solution for the first order upwind scheme. And as I said, you have some diffusion. Some of this unknown phi is diffused into our domain and then transported, and then you have the outlet. This here is just the last cell, so that's just cosmetics. So yes, he actually finds the solution. Now, if I jump to the central scheme, this one, same everything, and run the case, he blows up immediately. So he's much more jumpy. We have looked at the stability here. And we found out something, that the cell Reynolds number should be smaller than 2. And yes, that's actually what we are fighting with now with the central scheme. Upwind scheme, well, it's still a nasty problem, little nonlinear. So the stability analysis here is not that easy to do. So what I have to do now to make a solution, I actually have to use this over-relaxation factor to be an under-relaxation factor. Remember what he does. You have your unknown, and then you calculate an adjustment of this unknown to find a more suitable value. And in front of this adjustment here, you sort of multiply an omega. And an over-relaxation, well, then you overdo your adjustments. You sort of enhance it. But to here, I have to make things stable. So now I have to choose him very small. I think all the way down to 0.1 or something. Let's try 0.3. Oh, crashes. 0.2. Oh, crashes. So he's really jumpy. 0.1. I think I should get a solution. Yeah. So there we get a solution, but I had to reduce this adjustment down to only 10% before it was stable. So yes, you can use this omega as a stabilizing parameter when you have a nonlinear jumpy problem. So what should be the conclusion here? Upwind scheme, more stable. You get the solution faster. You could use a bigger omega, and he will still be able to handle it. He will find a solution. The error that I've printed out here, that is just the machine accuracy. I'm just solving the equations down to machine accuracy. So that's actually not so important. I only use the error here to tell whether it has succeeded or exploded. Remember, an error, it's a little stupid to solve everything down to machine accuracy, because when you do the discretization, the upwind scheme here, that was order delta x. The central, that is order delta x square. So you will always have an error anyway. So no point actually to solve it all the way down to machine accuracy, but never mind, I've done it so. Now, the actual physical error, I haven't plotted it, but you can see here from the book. Here are the results actually for the ISO lines here, gamma 1/100, 1/1000. So yes, you get the same results there. What is more interesting is these. So here they actually calculate the flux that should enter through this wall. You can do that numerically, and you can integrate up to have an analytical solution. So you sort of have a test value. And here it's just the number of cells you have versus the correct solution, what it should be. And you see clearly the central scheme has a much smaller error than the upwind scheme. Here is plotted also with a log-log plot, and you see the central scheme goes as a straight line with a slope of 2. So yes, this is a second order scheme. Smaller and smaller delta x, more and more accurate quite fast. The upwind scheme is all the way up here, first order slope, not good at all. And okay, smaller and smaller delta x will still get him smaller and smaller, but the second order scheme much better. So you have sort of something you have to decide for yourself. Okay, the upwind scheme is inaccurate but stable. You can get a solution faster. Central scheme, higher accuracy, much better. No, not so much false diffusion as we called it, but can be very jumpy, can be very unstable, can be hard to find a solution. So you have to choose here. The way you should think, in my opinion, is the following. Start with this one. Do a simulation here with the first order upwind scheme if you're only interested in a steady state solution. So this one is much faster. Then you will have a solution quite fast. It will be bad solution, but still you'll get it. Then you use this solution as a starting point for this scheme. Then he should be able to find his solution faster when he has a better input. Sort of an initial state that should be at least close to the final correct solution. So that could be one way to still use this first order upwind scheme. Any questions to this example? It's okay. A second example. This one is a little bit more fun. Also a classic test case. Very simple. So now we actually remove the diffusion term. We only look at the advection term. So in 2D, how does it look? Advection. You have U dphi x, V dphi y equal to 0. That's the two advection terms that we have in any two-dimensional case. And I say 0, no diffusion. And here U equals V equals constant. So they are sort of given, and when both are constant, equal to the same constant, that means you will have a flow of a 45-degree angle, like this. So this is the flow direction for the entire domain. And the advection equation now should represent just a scalar transport of this function phi, whatever that might be. Think of it as a concentration if you like. For the say the simpler test case, if you just be something on the side here. If I chose U equals 1 and V equals 0, then what? What kind of case do we have then? Well, you will have something like this. Just a constant velocity field hitting your domain, X and Y. And now, if this is U, say you now have a variation in this phi. It goes something like this. Say this is 0, and then I have phi equal to 1, and then I have a sudden jump, like that. So here I have phi equals 1, and down here I have phi equals to 0. So what would be the solution here for this problem? I don't have any v, so this one disappears. You only have this term. So it's a straight transport of this concentration phi. And the solution, well, no diffusion, so you should end up with something like this. Phi equals 1 and phi equals 0. It should not spray out. It shouldn't be smeared out, this sudden jump in phi. It should just be kept constant. And how will the discretization look? Well, for UDS, UDS upwind scheme, U is positive. You will have U multiplied with a derivative, first order upwind. That will now be Phi j minus Phi j minus 1 divided by one single delta x equal to 0. Which of course means Phi j equals Phi j minus 1. So yes, you get the correct solution directly. You don't even have to simulate it or anything. You see, for any position in the x direction, you just say the phi values, they are equal to the one to the left. Now if you use a central scheme, it will look something like this. Phi j plus 1 minus Phi j minus 1 divided by 2 times delta x equal to 0. How can you solve that one? Well, that's a tricky one because phi in the center point j, it doesn't enter into the equations. So of course it's possible here to cheat. You can rewrite it and say Phi j plus 1 equals Phi j minus 1. So you will sort of have the possibility to achieve the same solution there as well. But I would say in general, you will have coefficient matrix with the diagonal equal to 0, which according to mathematicians can't be solved. So let's do it like this. Not so funny. UDS has the correct solution, of course. Back to the test case. We have the velocity now going in the 45-degree angle. Then what? Then what? Let's see how it looks. Should be here somewhere. So here is the solution from the upwind scheme. I have a 100 by 100 cells. So yes, he can solve it. He can do it. But the correct solution should have been the same as we had when the flow was going horizontally. You see this smearing out of the value phi. I mean, here we now send in phi equals 1 on this boundary, phi equals 0 here. So we have a sudden jump. And this sudden jump should be sustained alongside this 45-degree angle. But you see the effect sort of has been smeared out over a substantial region. And it really doesn't help if you use fewer cells, say 10 by 10, would be quite crude. It really spreads it out. And if you say 1,000 by 1,000, if you can handle it. You It's getting better, but still you have this smearing out of the area. So what is happening? Now let's make it simple. We also say delta x equals delta y. I have the same number of cells in both directions. So how will the discrete version look like? Well, u and v, they are the same, and I have 0 on the other side, so they can be removed. Same with delta x and delta y can be removed. So I will be left with, for the Upwind scheme, UDS, I will have an x derivative here. It will be phi I comma j minus phi I minus 1 j. That's him. Upwind x derivative. And now here, upwind in the y direction must be phi I j minus phi I j minus 1 equal to 0. So this is actually the scheme that we have here. And when I program it, I just keep these two and say phi ij equals 2, and then fairly easy to have a forward loop solving this algebraic equation system. Why do we have this smearing out? Why is this effect here? Well, then actually we should do it like this. 2 delta x, 2 delta y, and then find the modified equation. How do we find the modified equation? Well, you take the Taylor series and insert wherever you don't have the center point. So you insert a Taylor series here and one here. And the Taylor phi, let's take that one, I minus 1 equals phi I plus delta x phi single derivative with respect to x. No, it's minus. Yeah. And then plus delta x square half phi double minus, and then higher order terms. So insert the Taylor series here, and what do you get? Actually, we should have these in front as well. Not that they change anything, we know them. So, okay, insert, and what do you get? Here you will now have u over 2 times delta x multiplied with uj minus the series, so he disappears. Then minus, and then he will survive. Oh, my mistake, it shouldn't be 2, it's only 1. You can see that now. Minus minus becomes positive, so you will have delta x multiplied with phi derivative, and then minus minus, so he will be negative delta x square half phi double, and then higher order terms. And you get the same in the y direction, v over delta y. Center point is removed, and then negative the entire series. So it will be this one first. Phi, what should we use here? Another color or something? Y derivative. I can write it like that. Y. Then this one minus delta y square half phi double derivative. Higher order terms. And yeah, on the other side equal to 0. So what will you get from the modified equation? Here you will have the first order derivative with respect to x, multiplied with u. So you will have u defeat dx from this guy. From this one, you will now have v defeat y. And this is very promising. We get back our original equation, as we should. Then we have some other terms. I throw them on the other side. And then you'll see, you'll have something like single delta x, single delta y. I just call it a delta. Delta half outside, and inside you will have double derivative with respect to x and respect to y, plus even higher order terms. So from the modified equation here, you can tell this is a first order scheme, because you have delta x and delta y here to the first order. The scheme is consistent. When you take lim, the deltas goes to 0, you get your original partial differential equation back. So that's okay. But here you see the effect with the upwind scheme. You get a double derivative here with a positive term in front. You get diffusion, you get viscosity where you don't want it, and you see the effect. He smears out these gradients, and the fewer cells, the worse. Let's try with 20. Yeah, looks terrible. So it should have been just this sharp jump from 1 to 0 alongside this diagonal. So upwind scheme, yes, possible to use, yes, stable, but very diffusive scheme. We don't like it. Now what will happen if I do this with an central scheme? CDS. Then we have 2 and 2, but here I need I plus 1 minus I minus 1. Here I need j plus 1, and there j minus 1. So you can do the modified equation for him as well. That will be okay. Then you will get third order derivative here. You will not get the second order derivatives, meaning this scheme, the central scheme, he will not add diffusion into the problem. But how to solve him? That is the problem. You see, the center point phi I comma j doesn't enter into the equation. So that one is a little bit tricky to solve. For this problem, it was possible to do it, not that hard actually, because you can start at this end or down in the corner if you like, and find the next point, sort of let the solution be transported through the domain. So you can find these two plus 1 and plus 1 here, based on all the neighbors to the left and the one under you. When you do that and solve it, you get, of course, what you should get. So it's possible to use the central scheme for this problem, although we have said earlier, for the pure advection equation, when you have 0 on the other side, central scheme are unconditionally unstable. Here, say by coincidence, we happen to find a solution. But in general, it will be unstable. As you can see from, say, the solution matrix here, you will have a diagonal with zeros. And that's normally a very, very bad idea. But it was actually possible, using the boundary conditions for this case, to find a solution. So as it says in the book here at the end. First order upwind scheme is inaccurate and should not be used. That's the conclusion. Sometimes we use them anyway. And you risk finding codes where this one is implemented. Maybe they don't like to talk about it. They have just done it so without telling anybody because it's so stable. You get a solution quite fast. But the solution is terrible, awful. So should never be used. But as it says, it's still in use in some commercial codes. We can use it to find a first tentative solution to a nasty problem, but you should never be the end solution. Absolutely not. Central scheme is the simplest, offers good compromise among accuracy, simplicity, and efficiency, although you risk it can be very unstable. Okay, any questions? Then we take a break and we play around with OpenFOAM a little bit afterwards.